Hello viewers, welcome once again to our probability class. Like I told you, this is a topic in Form 3, and so far we have done almost all of the subunits. What we are doing is that now we are looking at further exercises in what we are calling tree diagram. We are looking at further exercises in tree diagram. So this probability, and we are looking at tree diagram. Now, my name as your host is Geoffrey Omondi, and I hope we learn together. Now, in the last class in tree diagram, I gave you a number of exercises. There's an assignment I gave. So assignment from last class. So there's an assignment I gave, and that was exercise from KLB, exercise 13.4. I gave you number 1 all the way to number 6. So I want us to try a few of them so that you can see what you did from the last class. So I want us to try number 2. And it is important I write that question so that we are able to follow it from the write-up I will be able to give from this place. Now, the question was, so I'm reading from number 2, KLB, that is page 261. The probability of a horse, A, the probability of, it should be the probability that horse A, so this is not of, but that. So the probability that horse A wins a race against horse B is 2/5. If the horse runs 3 races in succession, if the horse runs 3 races in succession, find the probability, find the probability that horse A, so we can give them the first one, horse B wins all the races. Horse B wins all the races. Question B, horse A wins only 1 race. Horse A wins only 1 race. C, horse A wins at least 1 race. Horse A wins at least 1 race. D, horse B wins more than horse A. Horse B wins more races than horse B. So those are the questions we are dealing with. The probability that OS A wins a race against OS B is 2/5. If OS A runs 3 races in succession, find the probability that OS B wins all the races. OS A wins only 1 race. OS A wins at least 1 race. OS B wins more races than OS B. So when you look at this, especially in the first race, you realize immediately we are talking of mutually exclusive events, meaning that both horses cannot win the race at the same time. If horse A wins, horse B must lose. And if horse B wins, horse A must lose. And we say that when you're talking of mutually exclusive events, then the total probability is always certain, and it is 1. So the chance of horse A or horse B winning is actually 1. Now, I want us to try and draw that tree diagram together. Now, I want us to talk of horse A winning or horse B winning. So the chance of horse A winning, we are being told horse A wins is 2/5, 2/5. Now, these are mutually exclusive events. It means that their sum should therefore be 1. So if horse A is dealing with the 2/5, it means that we need 1 minus 2/5 to get the chance for horse B. And therefore, we will have 3/5, such that 2/5 plus 3/5 is 1. Mutually exclusive events. So that is the first race. Now, if horse A wins the first race, we can have a second race where we'll have horse A, horse B. Or if horse B wins the first race, we'll still have a second race, horse A winning or horse B winning. Now, the chances don't change. So in this case, horse A winning again will be 2/5, horse B winning 3/5, horse A winning 2/5, horse B 3/5. And we can create a third. Now, this is the second race. First race, second race, and now we are coming up with a third race. So in the third race, we'll again have AB, 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 and lastly AB, like that. So again here we'll have 2/5 for A and 3/5 for B. We'll have 2/5 for A and 3/5 for B. We'll have 2/5 for A in that instance and 3/5 for B. 2/5 for A and 3/5 for B. So from there, the most important thing now is to come up with what we call the outcomes. The outcomes. So to see this probably very well, I can use a different ink that will be able to give us. So this will be horse A winning, and horse A winning. That means that horse A is winning all the races. Or we can have horse A, then horse B. So horse A winning the first race, horse A winning the second race, then horse B winning the third race. Or we can have horse A winning the first, horse B the second, horse A the third. So that one will be horse A, horse B, horse A. Or we can have horse A winning the first, horse B winning the second and the third. So that will be horse A, horse B, horse B. Or we can have horse B winning the first, horse A winning the second, and horse A winning the third. So that will be B, A. Or we can have horse B, horse A, horse B. So that will be B, A, B. Or we can have horse B winning the first and the second race and horse A winning the third race. So that will be B, B, A. Or finally, we can have horse B winning all the races, which is B, B, B. So once you draw this, actually you've come up with what we call a tree diagram. Now, normally, even if you're not asked to draw, this will attract some marks, about 2 points, 2 marks for you having to come up with this, because this is very important, and almost all the responses we are going to give in successive questions depend on whether you are able to draw this tree diagram correctly. So if you come up with the wrong diagram at this point, then it's almost going to be impossible for you to get these responses correct. So I want us to start with the first one. Find the probability that OS B wins all the races. So this will be the probability that OS B wins the first race and wins the second and wins the third, like that. Probability of OS B, B, B. So when we look at that, we know that silently there are multiplication signs in between. That is what we know. This is actually how it should be written, but this is what we write, B, B, B. So in that instance, therefore, the probability of getting the first B is 3 out of 5, times the second B is 3 out of 5, times the third B there is 3 out of 5. Now, I'm using this branch because this is the only branch that gives us an outcome of B, 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 B winning all the races. So from that point, we can go ahead and say that this will be 3 times 3 times 3, giving us 27, over 5 times 5 times 5, giving us 125. So that becomes the probability of OS B winning all the races. Now, the second part B, find the probability of OS A winning only one race. Now, you therefore have to come to the outcomes here and look at a situation where we only have A winning one race. So starting with the first one here, we have A winning all the races. Here we have A winning 2 races and B winning 1. Here we have A winning 2 and B 1. In this instance, we have A winning 1 and B 2. So this is one of the outcomes we need. Here we have B winning 1, A winning 2. Here we have B winning 2, A winning 1. So this is another response we need. And lastly, here we have B winning 2 and A winning 1. This is another response we need. So when you look at all these responses, here the outcomes, when you look at all these outcomes, you realize that A is only winning once, which is what we need here, A winning once. So we'll start with the first one here, probability of A winning the first race, followed by B winning the successive 2 races. So we'll say it will be the probability of A followed by B, B, or this other one here, which is the probability of B followed by A followed by B, or the last one, probability of B followed by B followed by A, like that. So that is what we need. So from this instance, we can look at the probability of A, which is actually probability of A, which is actually 2 over 5, times the probability of B, which is 3 out of 5, times probability of B, 3 out of 5, or means plus the probability of B, which is 3 out of 5, the probability of A, which is 2 out of 5, and the probability of B, which is 3 out of 5. Or, and or here actually means plus. The probability of B, which is 3 out of 5, multiplied by probability of B, 3 out of 5, multiplied by the probability of A, which is 2 out of 5. So we can continue and shift that information here. Now, working with the 2 over 5, 3 over 5, and 3 over 5, we can solve this by saying 2 times 3, that is 6, and 6 times 3 is actually 18. So this one will give us 18 out of 125 plus, now, if you're keen, you'll immediately notice that the values that are being multiplied in each of these 3 brackets are similar, meaning the value answer you get for the first bracket is actually similar for all the three. So this will also be 18 out of 125 plus finally 18 out of 125. So bringing that information up, we agreed that if the denominator are similar, then you simply add the numerators in case of addition of fractions. So the response of that will be 18 plus 18 plus 18, giving us 54 over only one of the denominators, which is 125. At this instance, I don't think there's a common divisor for the two, so that will become our answer for OS A winning only one race. So we can look at part C. OS A wins at least one race. Now, again, we have to come back to our tree diagram, where OS A wins at least one race. Now, what that means is that OS A will win 1 or 2 or 3 races. So, what does that mean? Now, when you look at this place, OS A wins at least one, you'll realize that in the first instance, OS A is winning at least one because it's winning 3. He's present here, he's present here, he's present here. OS A is still present. OS A is here and OS A is here. So the only place where OS A doesn't win at least a race is a situation where OS B has won all the races, which is OS B, BB. Now, we agreed that these are mutually exclusive events. In other words, if we were to add all these outcomes, our answer is 1. So looking at this, and we know that where OS A is winning at least one race is all these values except BBB, we can therefore say that the probability of OS A winning at least one match, one race, that is, at least one race can be given by 1 minus the probability of OS B winning all the races, like that. So in this instance, therefore, we'll have 1 minus. Now, remember, we had already calculated OS B winning all the races, and our value was 27 out of 125. So that will be giving us 27 out of 125. Now, if we subtract this, therefore, our answer will actually be 98 out of 125. 98 out of 125. Those who are not very conversant with this, we will take LCM here, 125. Then 1 will go into 125 times 1. That will give us 125 minus. 1 will go into 125 once times 27, which is 27. 125 minus 27 is 98 out of 125. So that is how we've come with that value. So we can look at the last one. OS B wins more races than OS B wins more races. This should have been OS. Let me just check it to be clear. So OS B wins more races than OS A. OS B wins more races than OS A. So again, we'll come back to our tree diagram and find those instances where OS B has 2 or more. So when you look at this case, OS A has 1 more, OS A has 1 more, OS A has 1 more, OS B has 1 more here. So this is important, we pick it. OS A has 1 more, OS B has 1 more again, so we pick it. OS B has 1 more, so we pick it. And OS B has also 1 more. So from that instance, therefore, we can see what we need. So that is D. So that would be the probability of, the first instance is OS A, OS B, OS B. Or the probability of OS B, OS A, OS B. Or the probability of OS B, OS B, OS A. OS B, OS B, OS A, or the probability of OS B, all of it, the probability of OS B, which is probability of OS B, OS B, OS B. Now, there's something I want us to realize here immediately as we work on this. The probability of OS A winning more is the same as the probability of OS A winning only one race or no race at all. That is the same as the probability of OS A winning only one race or no race at all. Now, the probability, so we can say this is the same as the probability of OS A winning one race, or the probability of, so this is OS A, or the probability of OS A winning no race. So when we say probability of OS A winning one race, or the probability of OS A winning no race. So probability of OS A winning only one race, we worked it here, which gives us now 54 out of 125, or plus probability of OS A winning no race. Now, when we look at our tree diagram, the only instance where OS A is winning no race is actually where OS B is winning all the races. So that is similar to the probability of OS B winning all the races here. So, of course, you can see that OS B winning all the races, that was the first instance, is actually 27 out of 125. So when you work this one out, you get 81 out of 125. Now, there's something I want us to see, other than what I've just shown you here. We were able to come up with this probability very well. I want us to see that this probability you are seeing here and here, at this particular point like this, probability of ABB or BAB or BBA, you can clearly see it here. So we have to be keen when we are working so that we don't work twice. Now you realize that these questions can be very long in their responses. So you have to be keen to notice what you've already calculated so that you don't calculate it again. Again, probability of BBB, you are able to see that it is something we have already worked on here. So you simply pick those values and put it here. Now it is allowed. Once you've already calculated a value and you've been marked for it as correct, it is allowed you can pick that value and continue working with it without having to rework again every single value. So I want us to look at the next. I want us to look at next part of the assignment you are given. So that was number 2. I want us to straight away try number 6, which is also an assignment that was given to you in the last class. Number 6. I want us to try number 6. Now the question in number 6 was, a man playing a game of darts, has a probability of a third of hitting a double. Has a probability of a third of hitting a double. If he throws 3 darts, if he throws 3 darts, find the probability of him hitting. Find the probability, find the probability of him hitting A, two doubles, B, more than one double, and C, at least two doubles, So I want us to try that and see. So we will clean here so that we can try that. Now I want us to be clear that once the questions involving a tree diagram, the key is the diagram itself. If you have the diagram correct, normally you find it very easy to work with that diagram. So I want us to draw the diagram. So a man is playing a game of darts and is throwing 3 darts. So I want us to see the probability. So let the probability of hitting double be represented by H, and not hitting, in other words, missing, be represented by H naught. This is read as H naught. So we are talking of this H and H naught. So let us look at the first throw. So the first throw, we can have a hit or no hit, H naught. So we can also have a second throw with a hit or no hit. Third throw, hit, no hit. Hit, no hit, like that. Here, if the first one was no hit, the second can be hit or no hit. The third here can be hit or no hit, hit or no hit. Now, we are told that to hit is a third, meaning if this is mutually exclusive, to not hit should be 2/3. So to hit is a third. Not hit, therefore, should be 2/3. So that if you add a third to 2/3, you get 1. So we will have a third and 2/3, a third, 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 2/3, like that. So those are the probabilities. So it is important, therefore, that we get the outcomes. Now, remember I told you earlier that this tree diagram will earn you points because it's a very important part of marking your work. So if you draw it correct, it becomes very easy for you to answer what is required from you, and you will be rewarded for drawing it. There will be a point. So this one, the first outcome here will be hit, hit, hit. So H, H, H. Hit, hit, not it. So H, H, H naught. Or hit, no it, hit. So H, H naught, H. Or hit, not hit, not hit. So this will be H, H naught, H naught. Or no it, hit, hit. So this will be H naught, H, H. Or no hit, no hit. So H naught, H, H naught. Or no hit, hit. So this will be H naught, H naught, H, or no hit, no hit, no hit. So H naught, H naught, H. So those are the possible outcomes that we can have. So actually this is the sample space. This is what we are referring to as the sample space of this particular throwing of dart in 3 successions. So we can continue from there. And now using that tree diagram, we want to try and answer the questions that follow. So what is the probability that he hits 2 doubles? So this is A. So we are looking at a probability that we have 2 out of 3 hits. Remember, this particular player or man has thrown this dart 3 times. So if we ask what's the probability of 2 doubles, we are actually looking at probability of 2 hits. So if there are 3, only 1 should not be a hit. So we are looking at a situation where we have 1 hit not and 2 hits. So in the first case, we have all hits. Those are all doubles, 3 doubles. In the second instance, we have hit, hit, not hit. So these are 2 doubles. So this is one of the things we need. Here, we have a double, no double. So this is another thing we need. Here, we have 2 not hits, and therefore we don't need it. Here, we have 2 hits. Yes, it is another instance we need. Here, 2 not hits, we don't need it. 2 not hits, we don't need it. And here, everything was miss, not it, that way. So we are looking at those 3 instances. So we can come and say we are looking at the probability of, the first one is hit, hit, no hit. Hit, hit, no hit, like that. Or the probability of hit, no hit, hit. Hit, no hit, hit. Or the probability of the last one, no hit, hit, hit. No hit, hit, hit. Yeah, so those are the probabilities that we need from that point. Now, from here we can now work on them. The probability of hit, hit, not hit. Now, the probability of hit we have agreed is a third, and not hit is 2/3. So in this case, the probability of hit will be a third times the probability of another hit is a third times the probability of no hit is 2/3. Or means plus, and therefore probability of a hit here will be a third, no hit 2/3, hit a third. Or, which is again plus, the probability of no hit here is 2/3, hit a third, another hit a third. So these are the probabilities we are talking about. So from this instance here, we can now multiply and say we will now have 1 times 1 times 2, which is 2 out of 3 times 3 times 3, 27, plus the numerator is 2, denominator is 27, plus 2/27, giving us a total of 2 plus 2, 4 plus 2, 6 out of 27. Now we can simplify this further by knowing that 3 can cancel here twice, and 3 goes into 27 9 times. So that will give us 2 out of 9. So we can also look at more than one double. More than one double, number B. So number B, we are talking of more than one double. In other words, you are looking at one double, or we are looking at 2 doubles or more doubles. So it will be 2 hit, we are looking at 2 hit, that is 2 doubles, or 3 doubles to give us more than one double. So when we are looking at 2 doubles, we already have that, so that would be the probability of 2 doubles, or the probability of 3 doubles. Now, When we look at this, the probability of 2 doubles, we already have it in part A, and it's given by 2/9, or is plus probability of 3 doubles, meaning that is hit, 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 which can be given in this place like that. So that will be the probability of 3 doubles, hit, 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 like that. So from here, we can still work it out and find this 2/9 plus a hit was a third, the probability of another hit a third, and probability of the third hit is also a third. So working with this, we can therefore have 2/9 plus a third times a third times a third, which gives us 1/27. So we can get LCM here, which is actually 27. 9 would go into 27 3 times. 3 times 2 would be 6, plus 27 into itself once. 1 times 1 is 1, giving us a probability of 7/27. So this is a way in which you can be able to do it. So we can look at number C. Can look at number C. Allow me to do it here. Create a space here so that we are able to do it. We can work on it neatly like that. So this will be C. Now in C, we are looking at least 2 doubles. At least 2 doubles. At least 2 doubles. Now, when you say at least 2 doubles, it means that you are talking of 2 or more doubles. You are talking of 2 or more doubles. In other words, this means 2 or more doubles. But when you look at that keenly, it can also mean more than 1 double, because more than 1 double is actually 2 or more doubles. Now, when you are able to look at all this, what does it bring us back to? It means that at least 2 doubles is the same as more than 1 double. And therefore, in that instance, we've already calculated more than 1 double, and therefore our response is simply 7/27. So I want us to stop there for this class today. Meanwhile, I want to add you more assignments which you can try, and we can see if we can work them out in successive classes. I want to give you an assignment, and we'll see if we will be able to work them out in successive classes. In your assignment, please work on number. So this will be exercise. This will be exercise 13.4. You'll be able to work on number 9, number 10, number 11, number 12, number 13, number 14. Number 10, number 11, number 12, number 13, and number 14. Now, I want to appeal to you. Some of the times we can leave an assignment like this and you find you are not able to do it. Please feel free to go to the comment section just below this video and put your comment asking a question so that we can give you guidance on what is supposed to be done. You can also confirm with us and we give you a response. We can give you a worked example in the comment section so that you are able to work it out and follow what we have done. Otherwise, for now, I want to say goodbye. I was your host, Geoffrey Omondi. Have a nice time till we meet again.